just and then 30 seconds of introduction are just to recall what is the setting. The setting is the ARIA project. ARIA project is a project funded by European Union. And ARIA means Advanced Industrial Reduced Order Models, essentially. So the point of these seminars is to diffuse the information about the progress that we are doing in this project on one hand. On the other hand, these seminars have, let's say, a central occurrence, which are the ARIA conferences. We had 2 ARIA conferences, one in Bordeaux, the other one in Virginia Tech. The next one will be again in Bordeaux in 8th, 9th, and 10th of March 2023. And possibly there will be follow-ups in Stanford and probably in Atlanta. So this is the setting. I think that's about all of what I wanted to say. And now I leave Trajan to chair the session. Thanks, Trajan.
Okay, great. Thank you, Angelo. It's a great pleasure to introduce the speakers for this ARIA seminar. And our first speaker is going to be Juan Valverde, and he will be talking about non-intrusive ROMs for heat transfer and fluid flow problems in concentrated solar power applications. Juan?
Thank you, Trajan. Can you guys hear me properly, right? Perfect.
Yes.
So thank you for the opportunity. I'm really looking forward to show what we do in the industrial projects with reducer modeling. And I will start the presentation doing a very short introduction about the company. We're funded in 2010, and the core of the company is knowledge. And besides R&D, we develop industrial projects in both transport and energy sectors. We like to say that we bring data to the decision makers in both sectors. So we work a lot, as I said, in the energy and railway. And for instance, you can see here some pictures of data taking infrastructure like drones, and this is a onboard system on a train. And with this data and computational models, we are able to provide a knowledge to the clients in order to take these important decisions. So the company was a spin-off from the University of Seville, and the core, as I said before, is computational mechanics and numerical methods. But we have been working now for 12 years, so we have been changing a little bit the scope of the company. We do a lot of mechatronics now, and we put systems on industrial applications like the onboard systems, or the system that you saw on the energy market, like monitoring critical components. But basically, we are computational fluid dynamics and finite element people. And at the end of the day, we like to stick to our guns, and simulation is, as I said, the most important tool that we have developed in the company. Right now, we are 15 people. As I said, we do R&D and innovation, both in-house and outsourcing for large companies, and also industrial projects that benefit mainly from the R&D developments that we carry out, and basically energy and railways. All related to ARIA is more related to the energy sector, and there we work on the renewable generation, solar. We work a lot also on energy storage, thermal energy and thermochemical energy storage, and support to the plants. The solar plants, at the end of the day, are something new, and many problems arise that at the end of the day, the owners of the plants are not the technology developers, but big funds. So they need people to give them some advice on how to manage the assets from the operation and maintenance point of view. And we can say that we do a lot of consultancy, and we also develop our own projects and systems, both software and hardware. And for instance, in the concentrated solar power, which is the object of the talk today, so we have been working in many plants in Spain. We have 52 plants in Spain, and we have working in 50 or something like that. So we can say that we have covered mainly the whole market here. And also we have been working in the United States, South Africa, Middle East, Morocco, etc. So we have a let's say a good penetration in the concentrated solar market. These are some of the clients that we have, very important clients as Aqua Power. This is the biggest solar energy developer in the world. And for instance, this is the Redstone project. Is the last large concentrated solar power project that is being developed in South Africa. It's a big tower of 160 megawatts electrical, which means 600 megawatt thermal solar field. So the project is huge, and we have been working there on the storage system, okay, the molten salt storage system. So I will skip this quickly, and just a little introduction about CSP and thermal energy storage very quickly, if somebody is not familiarized with this type of technology. What we do is that we concentrate the sun rays with mirrors into, we can do it into a point, or we can do it into a line. So we have point focusing systems and line focusing system. This is a parabolic trough collector, and this is a central tower system. These are the most common technologies where we work on both of them. And with the storage that I'm talking about, mainly the only commercial storage system cost effective at the end today is thermal energy storage. You need to know that any project with batteries longer than 1 hour storage, we are talking here about 12 or even more hours of storage. Any project of energy storage based on batteries has been paid by the battery supplier, because nobody's going to pay 25 times the price of the thermal energy storage. So energy storage is still a problem to be solved if we want the renewable energies to penetrate, and not only solar, but every renewable which is intermittent and depends on the weather. We cannot control, so we need to uncouple the generation here in the tower or the parabolic trough from the demand, okay, and the electricity production. So the storage system can make this decoupling, so you can dispatch the energy anytime. So with a system like this, if we had more penetration of CSP with storage, we wouldn't have that many problems with gas right now, for instance. Well, so these are the commercial CSP projects around the world from the Solar Paces, which is the community around this stuff. And well, so now that I did this short introduction on this topic, as I said, we work a lot on R&D projects, and for instance, we just finished this HE 2020 project, which is related to thermochemical energy storage, with a big consortium, 14 members, and 5 million euros, and we were able to build the biggest pilot plant for thermochemical energy storage at the level of 25 kilowatts. It's TRL5. And what we do here is with the sun, we break a molecule. In this case, we can decompose into calcium oxide and CO2, limestone, or any material containing calcium carbonate. Okay, so you break the molecule, and you can store the products, and then when you put the products together again, they are going to be a very much exothermic reaction, so we can take the heat and put it in a power cycle. And the energy density of this compared to the regular thermal energy storage based on fluids, on sensible heat, is like 25 times more energy. And also you can use it as a seasonal storage, because the time that you can store is whatever you want. Okay, so these are some cut of the design of the plant that we did, the integration and all the solar part, the solar field, the tower, and all that. And you can see the plant here, which was built here in Spain. I may have some video over here talking about the technology and all that, but maybe you can check it out later. You can check it out later, probably. And area, of course, which you don't need any introduction for this. Also, this one that we have been doing with the National Renewable Energy Laboratory of the United States. I put this one here because this is the collaboration that we are doing with Professor Magdi Asayev from University of Bordeaux. We were there this summer discussing how to work in this particular project. This is a parabolic trough system, and usually what you have here is a fluid, that is a thermal oil, but we want to have the molten salts inside. The problem with the molten salts, the commercial molten salts, is that below 220 degrees, you are going to have the molten salts freezing. So you need like a huge electrical system to keep the molten salts in fluid state, because otherwise you will have a big problem. So the project is really changing the thing 160 degrees and let the molten salts freeze inside the collectors, and then doing very carefully a tracking of the sun. We are able to melt the salts in a way that we don't damage the receiver pipes. This is a receiver pipe, and this is the molten salts melting because of the sun heating the pipes, the receivers. So we have a 3D. This is a 2D simulation, but we need 3D simulations for this. Sorry, because we have like areas where we don't have a sun, so we need a 3D description of the problem. And the thing is that this takes like forever to be solved, like the order of weeks. So we are looking forward to reduce the time because it's really difficult to design or even to understand a process when you have to wait like a couple of weeks to have results. Okay, and other projects that we have are related to hybrid multi-demand multi-generation systems. Like this is a Spanish project, R&D, and we are doing a digital twin of the multi-generation multi-demand. We have a generation of hydrogen, electricity, steam, different things. I will show you. This is the scheme of the digital twin. So we have multi-generation, we have PV, we have a CSP, we have different towers with different fluids, and as I said, different demands, hydrogen, heat demand, electricity, etc. So if let's say designing a plant which relies on unknown source or intermittent source of the sun is difficult. So when you have many demands and many generation sources, you need definitely a digital twin to design the plant and also for the support of the operation. Okay, and also inside this project we are working on high temperature CSP receivers. At the end of the day, in top of the towers, what you have is a very critical heat exchanger. You have the radiation entering the receiver, and we need to heat up fluid most of the time. And usually the commercial stage is working on fluids like steam or molten salts. But in order to move to the next generation CSP, we need to work with other fluids that you can raise the temperature. So the thermodynamic cycle is going to be it's going to have a better performance, you know, if you raise the temperature. So we are working with a compressed air that we can raise the temperature up to 900 degrees, also with supercritical CO2 and things like that. At the end of the day, when you raise the temperature above 600 degrees, you need to put the receiver inside a cavity, because otherwise the radiation and convection losses to the ambient are too high. So you need a cavity like this. I will talk about these things later on the talk. But basically, just as an introduction, we need to calculate the heat losses due to the wind hitting the tower. This is the CSP tower in Morocco. This is the biggest solar plant in the world, and we have been working there many times. We took this picture actually, and we need to understand the heat losses, both convective and radiative heat losses. And one of the problems that we are working in area is the simulations for taking into account the convective heat losses to ambient from the receivers. This is external receiver, or from the cavity receivers, like the pictures that I'm pointing here now. And we also have other projects more in the industrial side, and not high temperatures and things like that, but things more, let's say, small, that we can, let's say, control, because we are a small company. And of course, we cannot develop a 500 million euros plant, but we can do the same things that we do in the large plants. We can do it in a big building or district, or things like that. So we work on the low temperature level, also to provide heat and cooling and heating demands for, as I said, buildings and things like that. And at the end of the day, it's the same complication, because you have many sources of energy, like the PV, the CSP, and different demands. You can have hot sanitary water demand, heating demand, cooling demand, electricity demand, etc. Okay, so we are working a lot on these digital twins. And this is the pilot plant that we are building. This is a project between Spain and Egypt. So we are building a pilot plant in Egypt. Okay. And these are simulation of the storage system that we are doing. This big tank here. This is I'm showing this because it's not on the area project, but we are now that we discover reducer modeling, we are using it extensively inside the company, and there are many places that you can use the reducer modeling, for instance, in this particular project. But what I'm showing here is a stratified tank, and this is a packet bed tank that we are modeling with ANSYS Fluent with porous media simplification. Okay, but this takes like weeks to do it, and we always have the problem that it takes a lot of time to do what we want to do our designs, to optimize the equipment. And So we have to live with these large periods of time. But now that we have discovered reducer modeling, we are entering a new phase where we can do things quicker and knowing that we are incurring in an error, but that we can control what we are doing. And then at the end of the day, the large simulation that takes forever, you can do it at the end of the day with the last model after you have designed and you have decided how is your system. And if you allow me, I would like to raise your attention today also to this doctoral network that we just got. I was about to send you an email to the partners of the project to do some publicity of the doctoral network. We have been granted with Marie Curie Action Doctoral Network, and we are offering 10 doctoral network positions. Okay, I will go to the one related to Virtualmech and University of Seville, which is this one, the DC one, and it's related to design of CSP towers and solar fields. It can be very interesting because we are going to be combining optics, fluid, thermal, mechanical simulations, and optimization. So it should be fun. And just if you have students that are willing to do a PhD, the only requirement is that they didn't spend in the last 36 months. They didn't spend 12 months in Spain. So we are very open to people from the ARIA network, and I hope it can be interesting for any of your students or somebody that you can know. So if anybody's interested, please send me an email. Okay, so after this large introduction, I would like to talk about a little bit about what we are doing right now inside the ARIA project. So I want to present the problem that we are working right now. As I said, we are working on the CSP tower receivers, and because we are working in high temperature applications like above 600 degrees, so we are gonna need to put the receiver inside a cavity. As you can see here, the receiver is composed. This is a cylindrical-like cavity. The radiation will come this way, as you can see here. This is a cone-like shape cavity, and this is a parallelepiped shaped cavity. And there are different approaches, and we are working and trying to look for the best approach for the applications that we are doing. That, as I said, is high temperature applications with non-conventional thermal fluids like compressor or even supercritical CO2. So basically, we are going to have this big tower with a lot of radiation heating, and then we will have this that we call receiver panels, which are a lot of small pipes that are carrying the fluid that you want to heat up, so the fluid can enter the receiver. Let's say, for instance, it is a particular design at 330 degrees, and it's getting out at 800 degrees. So we have a very big temperature jump, and we are reaching 800 degrees on the fluid, meaning that the steel, the pipes material, which is stainless steel and very expensive steel, is going to be like a 900 and 950 degrees. So radiation losses, which are at the temperature at the fourth, so are going to be huge, and you need to put the receiver inside the cavity. So you design the cavity and the receiver panels. So that's why we divide the problem into two parts. Although it's a coupled problem, at the end of the day, we need to decouple somewhere, okay? And we are decoupling with two different, we call it P1 and P2. For instance, this is a half cylindrical cavity. In the back walls, you will have the receiver receiver panels like this, where the fluid, the cold fluid enters a distributor, and then you put the fluid in many different pipes. You'd heat with the radiation here, and then you collect the hot fluid in a collector, and then you go to the thermodynamic cycle. So on the one hand, you have the problem of the heat transfer of energy from the radiation to the fluid, and you have on the receiver panels and the full cavity the problem P2, which is the convection heat losses to ambient. But also, if you want to solve P1 and P2, you need to couple. You need to solve in a couple way the heat radiation losses to ambient. So it's a kind of complex problem that we are trying to solve here. And at the end of the day, what we want to do is to optimize our design. So we want to optimize the receiver panels and also the cavity size or the cavity shape. So if we take a cavity like this is the aperture where you have the radiation, and also the convective heat losses come outside to the ambient from this aperture, and then we will have the receiver panels maybe on these walls, on the back side, on the lateral sides. So we need to solve this problem, these two problems, and try to optimize the shape of the cavity. So in order to do so, we can post optimization problem where we want to minimize the heat losses by convection, radiation, and the optical heat losses because you need to put all the energy in the aperture, and this is quite complex when you have a big solar field. Imagine that you have a heliostat like 1 kilometer away from the tower, so it's really difficult to target the aperture. So you have these heat losses, and the shape of the cavity and all the radiation and convection heat losses can be described in terms of fluid properties, many parameters like material properties, fluid properties, etc. And then your open variables will be the geometry. Okay, so we have the variable which is the geometry, and then we want to optimize with different constraints that we may have. So to do so, we are going to be evaluating the problem many times, and we need to reduce, of course, the computational cost of P1 and P2. Okay, so the thing that I want to show today is how we decrease the computational cost of the problem P2, and we are doing so with a non-intrusive ROM. The parameters, this is the cavity, and what we model is the air inside the cavity and the ambient air. This is our control volume. You can see the mesh here, and the parameters will be the velocity of the wind that is heating the tower and removing the air from inside the tower and removing energy. Also the temperature of the receiver panels that we call the wall temperature. And ideally, we want to change the size, but changing the size is quite complex, because you need to keep the mesh the same number of elements and nodes and things like that. So it's a little bit tricky, but we are working on that. But before we were moving these two parameters, the wall temperature and the wind velocity. And we did so with this tool, ACRB, which is from our partners from CISA. And just to give them the credit for the tool, which is really useful, and they have been very helpful, and they were always available for any doubts that we had. And basically, the two parameters, we have a range, and we divide in equally spaced the velocity and the world temperature. We go, this is Kelvin, we go from 973 to 1000, sorry, and we divide in five pieces the interval and also the velocity from 5 meters per second to 30 meters per second. And the snapshots, the full order model, we do it with ANSYS Fluent. It's important that you take into consideration that we are a company, so we use like a commercial software, so we need to introduce this that is operative with the rest of the, let's say, procedure that we have. So for us, when we take the snapshots, we put it in Python, and then we develop the solution and the parameter that we didn't know before. We need to plot properly. We need to see the results like we were inside Fluent. So we were checking the results with Python, and it was very not very convenient, but we realized that we have a ParaView for this thing. So we are plotting the data in ParaView, and we are automating the thing. And long story short, we with the different snapshots, we do a leave one out strategy to check out the errors, and we can reduce the computational cost like 10,000 times, because at the end of the day we are interpolating, not simulating. So you can find some big errors, but always they are very much controlled. This is the temperature field on the control volume. This is the inside of the receiver, and this is the ambient, and this is the full order model, reduced order model, and relative error in percentage. So I'm showing the largest result, the largest error, which is around 24%. But this is because we are taking the most critical. We are almost extrapolating, because we are taking the largest temperature and the largest and shortest wind velocity. Okay, so we can have errors of the order. This is for the second set of parameters, 13% and 24%. But if we go inside the intervals, okay, we can reach values of the error below 9%, which is really convenient for us, that at the end of the day, we are checking out how is the shape, how long is the receiver, and things like that, and we can live with an error of the order of 9%. So for us, it's been very, very helpful. And at the end of the day, if you go to other variables which are not so, let's say, stringent, like the pressure, we have a 3.2 or 1.4% error, which are incredibly small. And even for the velocity field, we have 2.5 and 1.5 error, which is for us is pretty amazing. So this works for us, and now we are trying to tackle the problem of changing the size and changing the mesh in order to be able to work with geometrical parameters. Okay, and before I finish, just 1 second, because we have been working a lot also with our partners from University of Seville, but this time with intrusive ROMs. So just to say that we are progressing in that, but they are the ones that should be showing what we are doing this particular regard. But we are tackling problem P1, and we started step by step with some benchmark problems. We started with an isothermal problem, but turbulent flow, which is the von Karman vortex problem. And then we moved to a problem with thermal energy, okay, non-isothermal, and laminar flow, which is a Boussinesq type problem. And both of them worked very well. And then we are moving to the real problem, which is turbulent flow and thermal. But this is another story that Thomas and his team will be able to talk any other day much better than me. And thank you very much for your time. Thank you.
Thank you, Juan. If anyone has a quick question, maybe in the interest of time, I think we're a little bit over time, but maybe one quick question before Michel gets ready to upload his talk. Any question for Juan? I don't see any. You can unmute yourself.
Maybe a very short question is concerning. So Juan, thanks for your talk. So what is the use of the leave one out method again? I didn't get it.
Basically, what we do with the leave one out strategy is that we compute 30 snapshots, and in order to see the error, instead of calculating another different snapshot at a different parameter, we subtract one snapshot and use it for calculating the error. And then we can do it very quickly on all the parameter values, and then we can see where is the highest error. So we have a better understanding on where to do the next full order simulation in order to improve the results.
Yes, sure,
okay?
Sure. Okay, thanks.
But this is all SISA development.
Okay, sure.
All for them.
Very good. Thanks.
Great. Thank you, Juan. Thank you very much once again. Very nice talk. Very informative. Thank you.